Hans-Peter, and I'd like to join all of the speakers in thanking the organizers for having this nice conference and inviting me to present our work here, and also thank you brave ones for staying for the absolute final talk of this meeting. What I'd like to tell you about today are experimental results from an experiment we started building in 2009, and it took us quite a bit of time to complete, and it belongs to a relatively new line of experiments people have been performing where people have interfaced a single or few ultracold trapped ions with a gas of neutral atoms. What you see here is actually an absorption image of a cloud of 10 to the 4 or a few times 10 to the 4 rubidium atoms. They're trapped inside a laser beam, so they're optically trapped. They're at a temperature of a couple of microkelvin. And overlapped with them, that's a fluorescence image. It's actually, the image is taken with the same imaging system, only going to two different cameras. There's a fluorescence image of a single trapped strontium plus ion. You might ask yourself, where's the dipoles involved in the gas? So the ion has an electric field. The electric field polarizes the atoms, and therefore they acquire a dipole moment. So it's actually, if you like, these are not dipole-dipole interactions, but rather monopole-dipole interactions. That's the dominant part of the interaction between them. Now, a good question is, where's the quantum part of that system? So they are very cold, and many of the degrees of freedom of both species behave quantum mechanically. Whether the interaction is quantum mechanical or not, you'll see for yourself. We're trying to work towards detecting quantum aspects of this interaction. Okay, so people have been trapping and laser cooling both ions and atoms for a long time, and both these fields have been very successful in exploring ultracold physics and many-body quantum dynamics. Ions are repel each other by the 1/r very strong monopole Coulomb repulsion. They're very cold, so they form these nice linear Wigner crystals in anisotropic traps. Each point you see here is a single trapped ion. There is really no overlap between the wave functions here. They're separated by micrometers, and the wave function at these temperatures is at the nanometer scale, which means quantum statistics doesn't play any role with these trapped ions. You don't really care whether they're fermions or bosons. They behave exactly the same. The interaction is so strong, really, it behaves quantum mechanical. So the interaction between them has no quantum aspects you can really detect. The quantum thing about their interaction, if you like, is the fact that they're phonons. The phonons of this crystal behave quantum mechanically. And in fact, we can cool this system or all the normal modes of this crystal to the ground state of the trap and then look at quantum behavior of these phonons. Again, the atomic structure plays no role in the interaction. They look like point charges, or it's a very, very small effect. Neutral atoms, on the other hand, are very different. So many systems work on the van der Waals 1/6 interaction, which can be modeled as a contact interaction. Physics happens at atomic scales, angstrom scales, where the wave functions overlap, and therefore quantum statistics is very, very important. So whether these gases are bosons and show Bose-Einstein condensation, or fermions and show degenerate Fermi statistics, you get a very different behavior. Once you have them cold enough, there's only one partial wave that participates in interaction, S-wave scattering wave. And actually, the atomic structure is very important. Actually, the atomic structure is the thing that determines the interaction between them. So the dipole moments and the quadrupole moments and so on that are formed in these atoms. And because of the large separations of ions from each other and the nice spatial structure, they're very good for performing coherent control. So people have been demonstrating, including our group, quantum computing protocols. They're very good as frequency sensors. They're among the best atomic clocks that you can have. They're very good for precision measurements. They're very, very sensitive sensors. Neutral atoms are, or most studies with neutral atoms have been about interactions, as we've learned in this workshop. People have demonstrated BECs. Fermi-degenerate gases have studied superfluidity both in Bose and Fermi systems. Dipolar gases have shown anisotropic quantum behavior. People have been looking at superfluid to Mott insulator and many more. So The idea is, why don't we take these excellent probes and immerse them in these many-body interacting gases and use them, if you like, as sensors, very local, very sensitive sensors of these many-body systems. Yes?
Probably way too early to ask this, but is this really just a sensor, or it actually polarizes and affects the properties of your many-body state? Because it's an ion, right? So
Yeah,
it's very long range.
Of course, it's never too early. It's a good question. The ion perturbs the atomic gas by polarizing the atoms. If it's a BEC or a degenerate Fermi gas, in a degenerate Fermi gas, for example, it'll display oscillations at the Fermi wavelength and so on. So of course, it's a perturbation of the gas. I think first experiments. So there have been some preliminary studies at UConn back at the early 2000s, but I think the first experimental results came out of the Vuletich group at MIT, and then at Michael Kohl's group in Cambridge, interfacing ytterbium plus with ytterbium and rubidium with ytterbium plus. I've listed here sort of 12. I hope I haven't forgotten anywhere. There's roughly between 10 and 15 experiments today around the globe, and about half of them look at the interaction of ions with atoms in a magneto-optical trap. So the temperature range, for those of you who know what magneto-optical trap are, is in the Millikelvin range or so, and the atoms are constantly excited to excited optical states. A magneto-optical trap is a trap where the atoms are constantly excited and cooled down by scattering photons. The other half of experiments is experiments where the atoms are in the ground state. They're trapped in conserving potentials like an optical dipole trap. In these traps, you can actually cool the atoms to microkelvin or below, where quantum degeneracy occurs, and you expect these experiments to present quantum mechanical effects more easily than these type of experiments, even though they're a bit more technically demanding. As you can see, the choice of neutrals and ions is rather democratic. I don't think there's been yet an experiment to repeat a choice of mixtures. And there are technical differences between the different mixtures. We work with rubidium strontium plus, and I'll discuss the consequences of this particular choice. So when people study cold atoms, they actually, by choosing the different system, they choose the interaction strength. Ions interact through the repulsive 1/r Coulomb potential. As I said, the just regular or non-dipolar gases interact through the van der Waals interaction, which is -1/6. Dipole-dipole interactions, on which we heard in this workshop, scale is 1/r³, and -1/r³, the potential or the scaling of the interaction is sufficiently long range such that you can never cool down to the S-wave scattering range. You can never cool down to even at zero temperature. All partial waves are involved in the collision or in scattering between two dipoles. Atom-ion interactions scale is -1/r⁴. That's the polarization potential, and that's basically the last stop. It's the softest potential possible with which S-wave scattering is still possible, where you can still cool down to a regime where there's a single partial wave, scattering amplitude is isotropic, there's a single parameter, the scattering length, which controls the scattering process. However, because it's a very soft potential, this happens at a very, very low temperature. So again, the ion polarizes the atom. It pulls the electron towards it. The dipole moment of the atom is proportional to the field, and the interaction is the field times the dipole, meaning the interaction goes like the field square. The field of an ion goes like 1/r², and the field square like -1/r⁴. So that's the origin of the 1/r⁴ potential. Yes?
So basically, for this potential, you can use this pseudo potential, like a point-like approximation with low energies, right? Because eventually only S wave would be important. But
at low enough energies, you can approximate as a contact potential, and then you have a single parameter in the scattering length. But unlike dipole-dipole, 1/r⁴ is the last stop. 1/r³, you can't do that anymore. But then again, because it's a very soft potential, the associated length with this potential is almost a micron long, meaning that the Broglie's wavelength of the two colliding particles has to be long as compared with that. And that happens for us, for example, at a temperature of 80 nanokelvin. So you really have to go down to very, very low temperatures to dive into this quantum regime of interaction. If you do that, then you have all the goodies that people have been looking at working with cold atoms, like Feshbach resonance. So for example, you can control very accurately the scattering length, meaning the interaction length between the ion and the neutral atoms. This is an example where controlling the scattering length was helpful in going through the BCS crossover with a degenerate Fermi gas. So that will be great to get there. And once you get there, people have had all sorts of proposals of using this system as an emulator for condensed matter physics. So for example, this is a proposal to use a chain of ions where the phonons of the ion chain are coupled to phonons in a BEC. And then the coupling between them would mimic the scattering of electrons by lattice vibrations. People have been thinking about using these ions as impurities, spin impurities, if you like, in this quantum degenerate gases and study Kondo-like physics or RKKY-like physics, where matter wave-mediated interactions mediate effective magnetic interactions between these ions. So it'll be very exciting to go down to this quantum regime. But there are some challenges on the way. Okay, so if you want to work on the system like this, which ions or atoms would you choose? Usually people like to laser cool and control alkaline-like atoms, or hydrogen-like atoms. For neutrals, this would be the alkalines here. For ions, this would be the earth alkalines after they're singly ionized. So many of the choices would be choices of guys from these two columns. We work with rubidium and strontium, which is really the same atom, only with one extra proton in the nucleus. We're working with strontium-88 and rubidium-87, strontium-88 plus. So the quantum numbers, everything is the same. The wavelengths are different just because the nucleus is more charged. So there's all the energy scales. But the mass is almost identical. So I've shown you the polarization potential. So there's the -1/r potential at long range. There's a core repulsion at short range, which is due to the interaction between electrons at short range. But really, if you choose strontium plus and rubidium, you have to plot all the energy levels. So this here is energy as a function of internuclear distance. And as I go to large internuclear distance, these lines should coincide with the quantum numbers of non-interacting rubidium and strontium plus, or strontium plus and rubidium, right? So an electron can be exchanged between the two. And in fact, if you look at the ground state of strontium plus and rubidium, so both of them are in the ground state, rubidium is in the ground state, strontium plus is in the ground state, we see this potential curve, but about 20,000 Kelvin below it, or at an energy, if I translate that to a wavelength of a photon, that's an IR photon of 800 nanometers or so, there's a much lower potential curve which belongs to neutral strontium and rubidium plus. And the reason that it's a much lower energy configuration, having strontium neutral and rubidium ionized, is because an ionized rubidium is a noble gas. All the electron shells are filled. I ripped off the single free electron it had. And strontium, neutral strontium has its electrons paired. So energetically, it's much favorable, which means it's an exothermic process for us to decay from this collision entrance channel down to a charge exchange channel, that lies way below. So again, we can go into the collision and out on the same channel. That would be an elastic collision, or we can go in and then, for example, exchange an electron between the two and leave on the charge exchange potential. That would be a highly inelastic process. If I look at the elastic scattering, then the first person to calculate the elastic scattering cross-section of neutral atoms from an ion was Langevin in the beginning of the 20th century. And he has shown that, actually, so if you look at the impact parameter of the collision, above a certain impact parameter, the atom and ion would simply be, this is a center mass frame, there will be a small deflection, but no close contact between the two. But below a critical a critical impact parameter, the collisions would be spiraling in and contact would be generated between the two. So inelastic processes, at least classically speaking, requires a collision below this critical impact parameter. Now, a very particular trait of the -1/4 potential is that the rate, the cross-section, if you like, goes like the square root of 1 over the square root of energy, meaning that the Langevin rate, the rate at which these Langevin collisions occurs, is energy independent. So as long as you obey this classical regime, you expect that the rate with which inelastic processes occurs, A would be either equal to or below the Langevin rate, which you can classically calculate. B, it would be energy independent. It would not depend on the energy of the collision. How do I tailor this classical description to the quantum description? Quantum mechanically, I can look at the Langevin rate as a sum over all different partial waves in the collision, and the cross-section would be proportional to the sine squared of the phase that was acquired during the collision, and I sum over all these partial waves. If I do that up to the maximal partial wave, which my energy allows me to, I get the Langevin cross-section up to a factor of 2. Actually, I forgot to say, this is within the semi-classical approximation with which I assume that I have enough partial waves here with non-correlated phases such that the sine square averages to give me 1/2. Okay, so that's the connection between this classical and quantum regime. In the S-wave scattering length, there's only a single partial wave and a single phase, and then this approximation breaks completely. So, you know, we want to cool down and look for signatures of quantum features in the scattering process. Here's an example for one such quantum process. If my collision energy matches a quasi-bound state above one of the centrifugal barriers of one of the partial waves, then I can get a quasi-bound state. This quasi-bound state changes the phase acquired during the collision. If you like, it enhances the time the atom and ion spend together, and then you can get a resonance in the scattering length. This is, if you like, a Fabry-Perot cavity for matter waves, in a sense. These resonances are called shape resonances, and there's a calculation here for rubidium with strontium plus for a certain inelastic process, which requires the two to be very close together. And you can see that this is a calculation by Olivier Dulieu's group. You see there's little resonances here, and these resonances go all the way up to 10 millikelvin, but their width is in the order of a few tens of microkelvin. So, I'm sorry? Just the S-wave potential, the bare potential, and the potential with the I'm sorry, the two colors here or the two colors here?
Here
in this figure?
No, the two potentials.
So the two potentials are just the bare potential without any centrifugal barrier, and the potential for one partial wave. This is a schematic drawing. I mean, it's not an accurate drawing. So with a temperature of a few tens of microkelvin, we might expect to see some quantum signatures. But I would say that in general, once you find a collision rate that happens in an energy-dependent way, that's already an indication that you departure from the semi-classical or the classical limit of your collisions. So that's something we would look for. Here's a layout of our strontium plus rubidium machine for the experimentalists in the cloud. We collect our atoms. So we have two vacuum chambers which are separated but connected by a thin tube. We collect about 1 million or 10 million or so rubidium atoms in a magneto-optical trap, transfer them to a far-off resonance optical trap. We evaporatively cool them to a temperature of a few microkelvin, and then we transfer them to another optical trap, which is composed out of the interference pattern of two laser beams which thread this apparatus bottom to top. And because these two laser beams have the same frequency, they interfere to give you an optical potential that looks like a 1D lattice. And now we vary the phase between these two lasers, and then we transport the atoms from the upper chamber 25 centimeters down to the lower chamber. If you like, it's a cold atom escalator. So within 300 milliseconds, we transfer them from the upper chamber to the lower chamber into the ion trap, in which a single strontium plus ion is trapped. And then in this experiment, in this science chamber, if you like, we transfer the atoms into a another cross-dipole trap. So their density is now homogeneous and not modulated by the lattice. And then we have a cloud of about 10 to the 4 rubidium atoms at a density of 10 to the 12 atoms per centimeter cubed, temperature of a few microkelvin. At these parameters, the Langevin collision rate between the ion and these cold atoms is at the kilohertz rate. That's the rate at which physics occurs. We initialize the ion in the ground state of the trapping potential, so for all practical purposes, 0 temperature, but with a 0-point motion due to confinement, or if you like, the ground state energy is roughly 50 microkelvin. So that's the starting point of the experiment. After we let them interact for a little bit of time, we turn off the laser field. The atoms just drop due to cavity. And then we can image the atomic cloud by absorption imaging and record the number of atoms and their temperature. And then we can also detect the ion. We can detect the state of the ion through fluorescence. And we also use either fluorescence or different types of interactions with laser fields to perform thermometry. All our thermometry methods rely on Doppler shifts, basically. If the ion is hot, it moves around the trap periodically, which means in its own frame of reference, the laser field is being modulated, and therefore the interaction with light is being modified. By detecting these modifications, we can extract the temperature of the ion. Now, as I'll show you in the next transparency, we need to work over a relatively wide range of temperatures, which means a single atomic transition is not sufficient for us, and we perform thermometry on 2 different transitions. One transition is it's a dipole transition. It's very wide, very strong, and this is a 20 megahertz wide resonance here with a little dark resonance, which is due to a repump laser, but that's just a detail. And the other line we work with is an optical clock line which connects the ground state of the ion with a D level. This is an electric quadrupole transition because S and D have the same parity. This transition has a lifetime of close to a second, and we have a laser with a line width below 100 hertz, so we can really detect this line with tens of hertz type resolution. So this would be much more sensitive to Doppler shifts than this guy. So this thermometer would be much better at low temperatures, whereas this would be used at high temperatures. So without getting into the details of the different thermometry methods, I'm just going to say that we had to develop methods that look at either the interaction of the ion with a narrow line width optical clock laser or with a strong transition, and we were able to cover this way about 9 decades or 8 decades of temperature. So from about 10 microkelvin all the way to about kilokelvin, with actually one blind spot here somewhere between, I would say 10 millikelvin or a few tens of millikelvin all the way up to almost 100 millikelvin. So we have about 1 dead decade here, but other than that, we cover 8 decades of temperature with these Doppler thermometry methods. Okay, so after I spent half my talk describing the system and the motivation, I want to go through a couple of experiments. I'm not sure I'll get to all of them, but what I'd like to discuss is elastic processes. So really, scattering is about exchange between 2 colliding parties. They can exchange momentum. As I've shown you, in our case, they can exchange an electron, so exchange charge. They can exchange spin, angular momentum, and they can also exchange an excitation, an electronic excitation. Okay, so the first experiment I'd like to discuss is that of momentum excitation. I think that's roughly what the atom feels at about a few microkelvin when the ion smacks into it. They're lost. They're gone. They don't stay in the trap. The ion is trapped in in 10,000 in 1 eV, in 10,000 Kelvin deep potential. So the ion doesn't go anywhere, but the atoms just go away. Okay, so elastic collisions, you might think that the story is pretty straightforward. You have a single ion. You can initialize it at whatever temperature you like. You have a bath of atoms at a temperature of a microkelvin. And then after a couple of collisions, the ion would thermalize with the bath, go down to the microkelvin temperature at which it's in the ground state of the trap, and everything is good. But there's one little detail. We do not trap our ion in a static potential. And the reason we don't trap our ions in a static potential is because Laplace equation forbids us from doing that. We cannot have just a 3D harmonic or any type of confining potentials. If we confine in one direction or two directions, the third direction should compensate for the curvature and anti-trap. So the way we trap is by using time-dependent potentials. This is a schematic drawing of a pole trap, of a linear pole trap. We have 4 rods. 2 of them are held at ground, and 2 of them are held at RF. So there's a potential oscillating at them, and that generates along the radial direction. So this direction we trap the atoms electrostatically without oscillating fields, but in the radial direction, it creates an oscillating quadrupole potential. And the oscillating quadrupole potential repels the ion, if you like, from the high amplitude RF fields to the low amplitude RF fields. So the ion is always being pushed away into the center of the trap where the RF amplitude nulls. The further the ion is away from the trap center, the larger is the RF amplitude. If it's at the trap center, given that the trap is well built, the amplitude of the RF field will go to 0. If the trap is not perfectly compensated, you're going to get this micromotion at the center. So if we look at the ion motion, we see that the ion motion has some harmonic motion, which is this sine function here. But superimposed on this harmonic motion, there's very fast driven motion. And the driven motion is in the frequency of the RF fields with which we trap. It's much faster than the harmonic motion. In fact, that's part of our stability criteria. So the ion motion has a superimposed micromotion, which is maximal when the ion is further away from the trap center. It goes to 0, and then it's being superimposed again. Now, how would this process of sympathetic cooling work in the presence of micromotion? So now the ion is hot, but it also has some driven motion on it. And when you have driven motion, you'll see that even though momentarily collisions between equal mass particles would take away all your kinetic energy, it can actually hit you up rather than cool you down. So what you see here is a map of a single particle oscillating around a 0 mean. This is velocity, from plus velocity to minus velocity. And at a given moment in time, it collides. And it loses all its velocity. But the drive continues to work. So now it will oscillate around a positive mean value. So collisions couple driven motion into harmonic motion. If you like, the work which is done by the pole trap is coupled into temperature. And the fact that collisions happen stochastically turn this into temperature, heat the ion up. Let me show you a phase-space representation of this process. So here I'm showing the ion in a 1D harmonic trap. We have velocity and momentum. So this is, velocity and position. So this is phase space. And the ion goes around this ellipse. And now what happens if this is a static, no driven, there's no drive here. This is just a 1D regular harmonic potential. If the particle collided, what happened? The velocity turned into 0 instantaneously. And the size of the ellipse would always shrink down. And this process would happen again and again and again until the ellipse would disappear. This is how sympathetic cooling works. What happens if the ion is driven by micromotion? Phase space of our pole trap looks like this. And this might look like a complicated trajectory, but in fact, you can think of the drive as tilting. If I plot all the points which occur at the same RF phase, I get these ellipses only tilted. So what the RF drive does is it takes this harmonic oscillator ellipse and it wobbles it back and forth, back and forth. Okay, this is a way to understand this complicated phase-space trajectory. Now what happens when collisions occur? If collisions occur at the 0 phase of the RF, I have this exact same phase-space trajectory as a non-driven harmonic oscillator. However, if the collision occurs at a pi/2 or 3 pi/2 phase of the RF drive, then depending on where the collision occurred, I can either be projected, again, instantaneously on 0 velocity, but onto a larger diameter ellipse, or if it happens close to the center of the trap to x equals 0, the ellipse would always shrink down. So now collisions stochastically either heat me up or cool me down. Fine, so we went out to measure this experimentally. We took our ion, we heated it up to a very large temperature, to about 200 Kelvin, and then we let it collide with the atoms that were at with the atoms. And if we heated up the ion axially, so along the z direction where there is no micromotion. There is no RF field. If you remember, our trap had a radial direction with which we use these RF fields to confine, and an axial direction where we do not. You see that collisions, these are the red events here, only reduce the energy of the ion. This is the distribution we get after an average of 1.4 collisions. Whereas if we start along the radial direction, you see that after, on average, 1 collision, we get events in which the ion cooled down, but we also get events in which the ion heated up, actually doubled its energy. Okay? So if the ion was heated up in this direction, we could get events where the ion, a collision rather than cooling the ion down, doubled its energy. So you might ask yourself, what is the type of distribution of energies that you get out of this process? And you soon realize that this is like an all-in casino, right? I mean, this process behaves in the following way. You take all your money and you bet it all. You either lose it all and you cool to the grounds to the trap, or you double your winnings. If you double your winnings, again, you have to win. You have to put it all in. And then you either lose it all, or I mean, in the extreme case, or you double your winnings. This is the multiplicative random process. And multiplicative random processes generate power law tail distributions. This is a distribution that you get when you simulate this process. These power law distributions are a hallmark of far from equilibrium complex systems dynamics. In fact, not just physical systems. The stock markets, casinos behave these ways. Earthquake starts this way. The distributions of cities in France follows a power law distribution, and so on. These distributions have diverging moments. This is the Thales form. Maybe some of you have heard of Levy flights. So there are various mathematical descriptions of these power law distributions. You can see that depending on the power law n here, the n minus 2, this is the density of states factor here, the n minus 2 moment, or I'm sorry, the n minus 3 moment of this distribution would already diverge. And if n equals 4, there's no average to this distribution. If n equals 3, then this is no longer a distribution. You just can't normalize it. So this is a pretty crazy statistical distribution of energies. The power law parameters depend on the trap, so the different trap parameters, the geometry of the trap, and so on. But they also, and the main dominating factor is the atom-ion mass ratio. If you take a very heavy ion and light atoms, n would become very large, would go to infinity in the infinite mass ratio limit. And when n goes to infinity, this distribution converges into being a simple exponential thermal distribution. So a clever choice, if what you want to do is go to low temperatures, is choose a very heavy ion, very light atoms. The stability, so if you take a very heavy atom and very light ions, then you go into these unstable regimes where stability occurs at about an atom which is 1.5 times heavier than your atoms. In our case, the atom and ion have exactly the same mass. So for us, n equals 4. So we're right on this edge of this crazy behavior before completely losing stability. Now, again, like in a casino, the fixed point is being bankrupt. So, the process I just described was such that if you lose all your energy, that's it. Game over, right? You just get stuck at the trap center and the process cannot continue. However, if something else keeps on seeding energy into the problem, then you would have, at steady state, some finite temperature, if you like, some finest T. And this seed can be different things. It can be the temperature of the atomic bath. It can be a non-compensated trap where the center of the trap still have some driving fields in it. What we've seen by looking at simulations is that while the bulk of the distribution depends a little bit on which of the mechanisms of seeding is at work, the power law is roughly indifferent to which of the mechanism is constantly driving energy into your system. So the question we wanted to answer experimentally was the following question. Let's assume your atoms are at 0 temperature. In our case, that's a very good approximation. They're at a temperature which is much below the ground state of the trap of the ion. And let's assume that your trap is perfectly compensated, which is again true in our case because we worked very, very hard to compensate the fields. So make sure that the center of the trap has vanishing RF amplitude or negligible RF amplitude. What would determine the energy of the atom-ion system. And this is a paper that came out of the Vuletic group by Marko Cetina, who suggested that the limit to at the lower bound to the energy would be determined by the following process. When the atom and ion go into the collision, the relatively long range minus 1 over r to the fourth potential would pull the ion away from the trap center into finite RF region. So the collision would occur at a finite RF region rather than the center of the trap. And because of that, energy would keep on being pumped into the process. So we went on and did the experiment. We cooled the ion to the ground state of the trap. We overlapped it with microkelvin temperature atoms, and we compensated micromotion to the 100 microkelvin range or so. And we measured by looking at the interaction with the optical clock transition, we measured the distribution of atomic energies that we get. And what you see here so I'm not going to go into the details of these curves. I'm just going to say that when you try to fit this data to a thermal distribution, you fail miserably. So the dashed lines here are trying to fit our data to a thermal distribution at increasing interaction times. And you see that as the interaction times becomes longer and longer, a thermal distribution is not a good fit. If we try to fit it to a Tsales distribution, we see that the Tsales distribution N, the power law, evolves as a function of time. But after roughly 5 to 10 collisions, Langevin collisions, N is being fixed at being equal to 4. And we see that the ion energy, or the mode of the distribution, the most likely energy, keeps on being heated as a function of time. The empty circles here are the results of a numerical simulation, which simulates this process, which is to a good extent a confirmation of this lower bound to ion neutral energies in pole traps. The next line of experiments I want to discuss is experiments where we looked at charge exchange processes between the ion and the atom. So as I mentioned, when the ion and atom go into the collision, they're not so when a strontium ion and a neutral rubidium enter the collision, they're not the ground state of the molecular system. The ground state of the molecular system adiabatically goes, when you separate them to infinity, into a configuration where strontium is neutral and rubidium is an ion. And when we let the atom and ions interact for a sufficiently long time, we see processes like this happen. How do we detect these processes? So we start with 2 strontium plus ions in the trap. And after a little bit of time, we see that one of them disappears. You see here? We start with 2, and then one of them disappears. But we know that there's an ion here. The reason we know there's an ion here is because the ion on the right side didn't shift to the trap center. It's still repelled to the side. The ion didn't move. So there's a dark fella here. It just doesn't fluoresce. So now we want to know what it is, whether it's rubidium plus or something else. And the way we do that is we measure the normal modes of the crystal. The normal modes depend on the mass. And we see the normal mode frequency. Even though the mass only changes by 1% or so, we see the normal mode of the trap shifts to the value that testifies that this is indeed a rubidium plus. And we see this process happens on average every 10 to the 4 Langevin collisions or so.
The fact that you don't see it is not enough to say that this is rubidium, so it's not the same property.
Well, maybe it's a rubidium strontium plus molecule. Maybe it's some hydride of strontium. You know, we're experimentalists. We need to prove that it is what we think it is, and it is rubidium plus. So how would charge exchange occur? So charge exchange can occur. There's a huge amount of energy that has to be dissipated. There are a couple of ways, or 3 at least conceivable ways for that to happen. One is through the emission of a photon, radiative. Okay. The other is by 3-body recombination. So that would be a collision, a 3-partite collision in which one of rubidium atoms would carry out the energy, kinetic energy, and go away, and then the 2 other would exchange this photon, or through some non-adiabatic potential crossing. So there'll be a big slide here. The 2 would go in, there'll be a potential crossing here, and the 2 would go out here. We don't see any potential crossing here, and we don't see the ions heating up too much when charge exchange occurs. So the 2 processes we wanted to differentiate are radiative and 3-body recombination. And to do that, we look at the reaction rate as a function of the density of the atoms. And because we see a linear dependence, we know that this is a radiative process. Okay, a photon is being emitted. We don't detect it. It happens very rarely, but a photon is being emitted and electron hops between rubidium and strontium plus. We'll get back to charge exchange in a little bit. The next inelastic reaction we looked at was that of spin exchange. So we interact our ground state strontium plus atom. The ground state, it's a single electron. This is an alkaline-like atom. It has no nuclear spin, so no hyperfine interaction. The ground state has two spin states. And we can polarize our ion whether to spin up or spin down at will. And then we can immerse our ion in an unpolarized sample of rubidium. And as expected from a spin interacting with a disoriented bath, the spin loses its direction after about 10 Langevin collisions or so. We see that if we start at spin up, the probability of spin up is 1, the probability of spin down is 0. We see that, probability of spin down is up, probability of spin up is 0. We see that after a sufficient number of collisions, the spin direction is being completely randomized to half and half. And now you might ask yourself, what is the physics behind this process? So one possibility is that of spin exchange. So the ion spin goes up, but that means that the rubidium electron spin goes down. What did I say? I said up, and then it goes down. So angular momentum within that two-spin system is still being conserved. The atom goes away. We don't detect it. And the ion spin is being randomized. Another option is that there is some coupling of spin, of angular momentum, from the spin part of Hilbert space into orbital angular momentum. And that would occur through some spin-orbit coupling, which would induce spin relaxation. So we want to differentiate spin exchange from spin relaxation. In a previous experiment from 2013, the Coulomb group has measured a terbium plus rubidium mixture and have shown that their spin dynamics was dominated by relaxation, by strong coupling of spin to the external degrees of freedom, of angular momentum to external degrees of freedom. So how would you differentiate spin exchange from spin relaxation? Well, there's one efficient way of doing that. You align your atomic, you polarize your atomic bath, and you polarize your ion, and you polarize them in the same direction. So now the rubidium spin and the ion spin are parallel. In this case, exchange cannot work, right? There's nothing to exchange. They point in the same direction. And that, if spin dynamics is governed by that, that means we'll see a significantly different behavior when we align them parallel or anti-parallel. Rubidium has a hyperfine structure, and that means that in order to polarize it, we need to pump it into the hyperfine stretched state, where the nuclear spin and the electron spin are parallel. In this case, it will be the m equal 2 of the f equal 2 manifold of the hyperfine state, or the 2 minus 2 if we want to point it down. The ion would be pumped into the minus 1/2, and then we'd look at the dynamics. And when we do that, we look at the temperature. We see that when we do that, this is the fluorescence curve again, we see that the ion heats up to about 17 millikelvin. What does it mean? It means that some hyperfine energy is being released occasionally into the cloud. The hyperfine energy in rubidium is 330 millikelvin. It means it doesn't happen too often, but it does happen every once in a while. That means that we do have some spin relaxation at play. But if we initialize our ion in the 2,0 state, we see that we get about a 3 times hotter temperature. What does that mean? It means that while spin relaxation is at play, spin exchange is stronger. So our dynamics is dominated by spin exchange, but we're not free of spin relaxation. Okay? So now we would like to go ahead and measure the spin direction directly, like we did before. The problem with doing that at 17 millikelvin is that it's too hot to directly measure the spin for technical reasons. So in order to do that, we went ahead and polarized the atoms in the F equal 1 manifold. Now in the F equal 1 manifold, the electron has 2 components of spin, both spin up and spin down. But they're arranged such that if you flip the electron spin, you have to change your hyperfine state. And that costs too much energy. Our sample is too cold to pay that 330 millikelvin endothermic price. Okay? So we're protected by dynamics. And when we do that, we see that when we immerse a rubidium ion In an atomic cloud, which is polarized in the 1-1 state, the ion spin is being collisionally pumped at the 90% level to align itself with the bath. Okay, collisions align the ion spin with the direction of the bath. Why are we limited to the 90% level? The reason we're limited is spin relaxation. So there is still a finite rate of it takes about 7 Langevin collisions for spin exchange to occur. It takes about 40 Langevin collisions for spin relaxation to occur, which is kind of in agreement with a ratio of 3 in the temperatures that we measured before. Yes?
This small error on the left diagram that points from -1 to 0, when the F equals 1, is this an allowed? When you do pump the atoms to the -1, can they go to 0?
When I pump, well, depending on the spin state of the ion. If the spin state of the ion is anti-aligned, then you can, so depending on whether the ion is in the up or the down states.
I thought you said it could only go up.
No, I mean, so one direction is protected by exchange, one direction is protected by the energy gap between the two hyperfine states. When we immerse the ion in when rubidium is prepared in the 1-0 state, which is not aligned with any of the directions of the spin of the ion, we see that the ion decays into an equal mixture of spin states after about 7 Langevin collisions or so. So back to, so spin exchange, again, how can you understand the process? We're dominated by spin exchange. What would be the physics that would explain the way spin exchange works in the system? And there's actually a very simple way to think about it. When the strontium ion or the 2 electrons enter the collision, when they go to a sufficiently short range, the exchange or the Pauli exclusion principle plus Coulomb repulsion, what people call exchange interaction, not to confuse with the spin exchange, well, maybe you can confuse it with the spin exchange we see here, but it lifts a very large gap between the singlet and the triplet manifold. So this upper curve here is the singlet molecular potential, and this lower curve here is the triplet molecular potential. Okay? The way spin exchange occurs is if we enter the collision in the up-down state, we're actually at a plus superposition of the singlet and the m=0 state of the triplet. Whereas if we're at the down-up state, there's destructive interference between these two guys. Now, during a collision, the phase between colliding on the singlet and the phase between colliding on the triplet is different. So even though you start in the up-down state, you acquire a difference of phase between S and T simply because you collide on different potential curves. And this phase shift would flip your spins. So if I want to know what is the spin exchange cross-section, again, I have to sum over all partial waves and look now at, rather than in the Langevin case where I was looking simply on the sine square of the phase which is acquired on the potential curve, now I look at the sine squared of the phase difference between the singlet and triplet. Now if I align my two spins, I only populate the triplet state. I have no amplitude on the singlet, and that's why spin exchange cannot occur. If we go through this naive calculation with model potential curves, again calculated by Olivier Delou, we get under the semi-classical approximation that these phases randomized to about 1/2, we get a rate which should go like Langevin over 16, which is in a factor of 2 agreement with what we measure. Now back to charge exchange. So we know now that we're dominated by spin exchange. That means that if we start with parallel spins, i.e. on the triplet manifold, we remain on the triplet manifold. That's one piece of information that I gave you. Another piece of information that I gave you is that charge exchange happens radiatively. We enter the collision on this molecular potential belonging to strontium plus and neutral rubidium. A photon is being emitted, and then we exit the collision at the curve which belongs to neutral strontium and rubidium plus. Now we know that photon emission cannot change the spin symmetry of the system. That is because without any spin-orbit coupling, the photon doesn't couple to the spin degree of freedom. This is a dipole transition. It only couples to the electron motion, not to its spin. So we would expect that by controlling the singlet and triplet overlap of our collide wave function, we would be able to control the charge exchange rate, the reaction rate. And that's actually exactly what we see. So when we look at the charge exchange rate, when we initialize our bath, our rubidium bath, in the 1 - 1 state and the 1 0 state, where the ratio of singlet overlap is about 1.5. And again, charge exchange can only occur by emitting a singlet. Actually, that's one point of information I forgot to say. The ground state here is the ground state of a neutral strontium, which is a singlet. Okay, so the ground state here doesn't have any triplet. It's only a singlet. And that's why photon emission can only connect the singlet here to the ground state. It cannot connect the triplet. So when we compare two atomic states where the steady state has a different overlap with a singlet state, we see the exact same ratio in the charge exchange rate between the two cases. So this is a really nice example where you take a single atom, and by controlling its spin direction, you can actually control the rate at which a chemical reaction is occurring. So it's kind of neat. Okay, I have 10 more minutes, so the last topic I would like to cover is another exchange during a collision, another inelastic exchange, and that is the exchange of an excitation. So all the experiments I've shown you so far, both the ion and the neutral have entered the collision on their electronic ground state. The S, 0 orbital angular momentum, and the lowest quantum number, which is allowable for these guys. What happens if we enter the collision where the ion is excited to a metastable state? And the state we excite it to is the excited state of our narrow line with optical clock transition. So as I said, the lifetime of this level is about 0.4 seconds. So it's rather long-lived as compared with the kilohertz rate, collision rate that we have, Langevin collision rate that we have with the atoms. The motivation for doing that, by the way, is that we would like to perform spectroscopy of this optical clock transition in the presence of atoms and look for the shifts of this relatively narrow, few tens of hertz, narrow line. So, you know, the interaction between the, if you like, the quadrupole dipole interaction between the ion and the D state, which does have a quadrupole moment, and the induced dipole of the atoms should shift this line, and that would give very nice and clean tool to investigate the dynamics during the collision. But in order to perform this experiment, we would first like to know what is the T1 time, if you like. What happens when we initialize the ion in the D level, but then put atoms in its vicinity? Do the atoms quench the D level? What happens? And in two previous experiments, again, Cole group back in Cambridge and Mukayama group, which is now in Osaka, have looked at this process for different mixtures, terbium plus rubidium, and lithium and calcium plus. And in both cases, they've seen that charge exchange happens immediately when you let the atoms interact with an ion in the excited state. That's not extremely surprising, because if you look at the potential curves here, there's this huge spaghetti here. The D level is somewhere here. So there's so many level crossings here. It's hard to imagine that you wouldn't get a level crossing with the opposite charge and just adiabatically, non-adiabatically roll down into this new charge exchange state. So we did this experiment. What you see here is the probability of being in the D without atoms and with atoms. And you see that with atoms, the probability of going down to the D is being shortened to the, you know, on the rate of 2 collisions or so, 2-3 collisions. So it's 1 to 2 milliseconds, and the ion is already down. So it's almost universal. It doesn't happen every Langevin collision probably, but every a small number of Langevin collisions. Furthermore, we see no charge exchange or ion loss. So unlike these previous two experiments, we don't see the charge exchange occur. That's good news for us. That means we can repeat the experiment over and over again without having to reload our ion trap, which is always a nuisance. But something else we notice is that every time we do that, the ion heats up tremendously. Fluorescence simply disappears, and we have to measure the rate at which it cools down to estimate the energy it acquired during this quench. And when we do that, we see that this is a histogram of the energy we measure after the ion quenched. And you see that there are 2 peaks to the distribution. One peak is centered around 1500 Kelvin, which is pretty wide, mostly probably due to inaccuracies in our thermometry method. Our thermometry is not extremely accurate when you go to 1500 Kelvin. And another narrower peak at around 200 Kelvin. And when you know these energies, you identify the channels which are involved immediately. The 200 Kelvin is the fine structure splitting between the D5 halves and the D3 halves levels, which means there's some spin-orbit coupling which transfers the ion from the D3 halves to the D5 halves. There's 400 Kelvin gap between these two states. And because we're talking about equal masses, the ion takes away half that energy, 200 Kelvin. And the 1500 Kelvin is the exact half, or 2 times 1500 Kelvin, 3000 Kelvin, is the exact difference between strontium plus being in D and rubidium being in S, and strontium plus being in S and rubidium being in P. I know there are some rubidium coolers in the room. Rubidium being in the P, that's the 780 or 795 lines with which people build the rubidium MOT and so on, laser cooled rubidium and so on and so forth. So what we see here, and this is supported by a preliminary calculation of potential curves, again by Olivier Deloux, which shows a very clear level crossing here between this entrance channel and the channel here. So really an excitation, an electronic excitation is being transferred from strontium plus into rubidium. Rubidium then decays. The lifetime of the P level is a few nanoseconds. It decays. We don't see that photon, but we see the kinetic energy which is being released in the process. Just to verify that our interpretation is correct, we repeated this measurement when the ion is initialized in the D5 halves and the D3 halves, and we see that when we initialize in the D3 half, the 200 Kelvin peak disappears. And again, because when we start in the D3 halves, the ion doesn't have enough energy to climb up these 400 Kelvin, this reaction cannot occur. So this is a verification that the 200 Kelvin is indeed due to transfer between the two fine structure levels. So this brings me to the summary. As you can see, this is a young field. We're now busy, rather than looking at many body physics, which is yet to come, we're still investigating the bipartite interactions, the inelastic processes, the elastic processes. There's actually a lot to study. I think there hasn't been one experiment we did here without being surprised. I don't know if it testifies on the experiment on us. But we keep on struggling understanding what we're seeing, and that's a lot of fun. Working with trapped ions, you simply know what you need to get, and you better know, because if you want to build a quantum computer, you better know your system with like 6 digits of accuracy. And here, we don't know much. We plan to continue to study spin dynamics and perform optical clock spectroscopy and non-equilibrium dynamics. We want to start, in particular, look at the energy dependence of all these processes to start looking for quantum signatures and deviations from the semi-classical or the classical regime. We've already seen preliminary indications of that, which I haven't told you because they're very preliminary. So look for shape resonances, in the future Feshbach resonances. To be more efficient, we have to go colder. And in pole traps, the roadmap is pretty much blocked. It'll be very nice non-equilibrium statistical mechanics, but it doesn't going to get us down to the S-wave scattering regime, and probably there we'll have to move into optical trapping of the ion rather than using the pole trap. We'll just transfer the ion to the same trap that holds the atoms. It's a challenge because any stray electric field will apply forces which are multifold as compared with that of the optical typal trap. So you have to control your electrostatic environment on an extreme level. Another option of going quantum is exploding the interactions. So for example, if we'll dress a rubidium cloud with a Rydberg dressing, we'll take the rubidium polarizability to the sky, and then the interaction time scale would go to the megahertz or even hundreds of megahertz range. And in this case, it doesn't really matter whether you're at the millikelvin or at the microkelvin. Things just happen too fast. So that's another outlook for these experiments. Before I finish, I'd like to acknowledge, and so even though I'm talking about these things, I didn't do any of these experiments. They were all done by a bunch of brave PhD students. Ziv Meir, Thomas Sikorsky, Ruti and Merav who are here, and Nitzanu is here, Yoni Dalal. And I'd like to thank all the other members of the ion trapping group. I'd like to indicate that we've recently inaugurated a center that can, or I shouldn't say center, but a roof that consolidates all the AMO activity at the Weizmann Institute of Science, and there's a lot of AMO activity. And this entity does offer available postdoc positions, so go to this website and check it out. And I'd like to thank you for your attention.